Hello everyone, welcome back to AE NVGO 123. This is assignment 9. In assignment 9, we are going to practice circuit analysis in phasor domain. Question P 5.22. Suppose that V1 is equal to 100 cosine omega t and V2 is equal to 100 sine omega t. Use phasors to simplify the sum of them to a single term in the form of Vm cosine omega t plus theta, and draw a phasor diagram showing V1, V2, and Vs. And we are also asked to state the phasor relationships between each pair of these phasors. Let's first convert V1 and V2 into the phasor form. So V1 t is equal to 100 cos omega t is equal to 100 the angle of 0 degrees, and V2 t is 100 sine omega t. Because this is omega, what we need to do now is first convert it into the cosine. So that is 100 cosine omega t minus 90 degrees. Well, we can draw a cross here and see how to convert by using the trigonometric identities. This is negative sine, negative cosine, and a cosine. Here it is at the sine. So we go clockwise direction for 90 degrees. That's minus 90 degrees. So convert the sine into cosine. We can express it as 100 cosine omega t minus 90 degrees. So that's V2. And we can write it as 100 angle of negative 90 degree. Well, we wanna add V1 and V2 together, but it's not easy to add two expressions in polar form together. So what we need to do now is to convert them into the rectangular form. So 100 the angle of 0 degree is 100, and negative 90 degrees is negative J100. Well, so how should we convert? Well, we know that to convert between the polar form and the rectangular form, we have some formulas. When we have the expressions in the polar form, z is equal to x plus jy. And we want to find out x and y. Here we have x is equal to r cosine theta, y is equal to r sine theta. And when you substitute in theta as negative pi over 2, and here theta as negative pi over 2, the x will be 0 and the y will be negative 100. So that's how you get this value. So now what we need to do is to find Vs. To find Vs, we need to add them together. Vs is V1 plus V2, and that is 100 minus 100J. Well, now what you need to do is to convert this back to the phasor form, and you'll get 141.4, the angle of negative 45 degree. Well, so how can we do this? When we are converting the rectangular form into the polar form, we can also use some formulas to find r and theta. To find r, we can use the formula r is equal to the root of x squared plus y squared. and theta is tangent of the arctangent of y over x, so that you can find this value. Because we need to convert it into the form in the time domain, so we need to write as 141.4 cosine omega is, we don't know the omega value, but we can write it as omega t plus, here is plus negative 45 degrees, so that's negative 45 degrees. So this is our answer for this question. We are also asked to draw a phasor diagram showing V1, V2, and Vs. Let's first draw V1. V1 is 100 the angle of 0 degrees, which means that the angle between the horizontal axis is 0, and R is 100. So let's draw it. This is 100, and this is 0 degrees. Have no degrees, no angles between this angle with the horizontal axis. So this is 0 degree, and this is V1. Now let's draw V2. V2 has an angle that's negative 90 degrees. So we go clockwise direction. This is 90 degrees. And same, R is 100. Amplitude is 100. So this is 100, and this is V2. Now let's draw Vs. Vs has an angle of negative 45 degrees. So this is negative 45 degrees, and this is 141.4 as R. Well, we are also asked to state the phase relationship between each pair of these phasors. So the phasor relationship describes which phasor lags and which leads. So we have three phasors, so we can write three relationships to describe their relationship. Well, first let's observe the relationship between V1 and V2. Well, V2 is here. It has an angle of negative 90 degrees with V1, which means that V2 lags V1 by 90 degrees. So we get the first relationship. V2 lags V1 by 90 degrees. Well, let's see for V1 and Vs. Well, Vs has an angle with V1 as negative 45 degrees. So Vs lags V1 by 45 degrees. Well, finally, let's observe the relationship between Vs and V2. Well, here we can see that actually V2 has an angle with Vs as negative 45 degrees. So we can see that V2 lags Vs by 45 degrees. But we can describe this in the other way. If we say that Vs with V2 has an angle of 45 degrees, we can also say that Vs leads V2 by 45 degrees. So that's the relationship between V1, V2, and Vs. Question P5.32. A voltage VL is equal to 10 cosine 2000 pi t, and this voltage is applied to a 100 millihenry inductance. So we know that the voltage value VL, and we also know the inductance L. What we need to do here is to find the complex impedance of the inductance. Other than that, we also need to find its voltage current in the phasor domain, and draw a phasor diagram. And we also need to write them down in the time domain and draw the voltage and the current with respect to time and state their relationship. So let's first find out the complex impedance of the inductance. It's actually pretty straightforward. We only need to substitute in the formula we have. So for capacitors, we have, let's recall, ZC is equal to 1 over j omega c. For inductance, ZL is j omega L. So let's substitute the numbers. ZL is j omega L, that is j times 200 times pi, that is 200 pi, the angle of 90 degrees. So we found the impedance. Now let's find the voltage. The voltage is given to us in the time domain, but it's very easy because it's in cosine. In cosine, we can easily convert it to the phasor domain. We have L is the amplitude 10 and the phase 0. That's 0 here, so that's 10 angle of 0 degrees. Now let's find the current. To find the current for impedance, we simply apply Ohm's law. IL is VL over ZL, and substitute the number, you get 1 over 20 pi, angle of negative 90 degrees. To write the current in the time domain, ILT, we first need to find what's the omega, the angular frequency, right? The angular frequency is actually here. That's omega is 2000 pi. So the amplitude is 1 over 20 pi. So that's right. 1 over 20 pi times cosine, the angular frequency 2000 pi. T, the phase is negative 90 degrees, so minus 90 degrees. So what we can see here is that the relationship between the current and the voltage. We see that the phase for the current is negative 90. For the voltage is 0. So we know that the current ILT lags VLT by 90 degrees. Now we can draw the current. We can draw the diagram for both the current and the voltage. We need to sketch the voltage and the current to scale versus time. So let's draw it. This is T, this is V or I for the inductor. Because the voltage leads the current, so it should start early. If we base on the current waveform, let's draw it like this. It should start early, so it should be here. 90 degrees is pi over 2, so it should start here and end here. And this one is the voltage. This one is the current. Well, one thing to keep in mind here is that I skipped a step here. Here, the omega is 2000 pi, and L, actually I directly use 100 times 10 to the negative 3 Henry. So if we simplify, we can get to the expression like this. Question P 5.33. A voltage V is equal to 10 cosine 2000 pi t is applied to a 10 microfarad capacitor. So here, actually, this question is exactly the same as the last question. The only difference is now it's a capacitor, not an inductor. So we actually can follow exactly the same step. First, omega is 2000 pi, the same as the last question. And we need to find the complex impedance, that's ZC. ZC is 1 over j omega c. And if we substitute in the values, we can get negative j 15.92. And in the polar form, that's 15.92, the angle of negative 90 ohm. Now, we need to write the voltage in its phasor domain. That is, V is 10, the angle of 0, 10 is the amplitude, and there is no phase. The phase is 0 degrees. To apply Ohm's law, we can find the current IC, that is VC over ZC. And you substitute in the value, you can get 0.6283 angle of 90 degrees. And convert this into time domain. IC is equal to 0.6283 cosine 2000 pi t plus 90 degrees. Well, so here the current is plus 90. The current has a phase of plus 90. For the voltage, that's 0. So we can clearly see that the current leads. So the current IC leads VC by 90 degrees. Well, this is actually a common rule for the capacitors and the inductors. For capacitors, current always leads the voltage across the capacitor by 90 degrees. And for inductors, that's the opposite. The voltage always leads the current by 90 degrees. So let's draw the voltage and current with respect to time. So this is T again. And because now the current leads, let's first draw the voltage. This is the voltage, and the current leads 90 degrees. So the current actually starts here. So the current looks like this. Be careful about the amplitude. The amplitude for the voltage and the current is not the same. Question P 5.34. A certain circuit element is known to be a pure resistance, inductor, or capacitor. We need to determine the type and its value. We know the voltage and the current. So what we need to do is to find an impedance. With impedance, we can determine the type very easily. So question A, Vt is 100 cos 200t plus 30 degrees both. It is 2.5 sine 200t plus 30 m. Let's first convert them into the phasor domain. So this will be 130 degrees. Be careful here, this is sine, so that's 2.5 cosine 200t minus 6 degrees. And this is 2.5 negative 6 degrees. So C is V over I, and substitute the value, we can get that's 40J. And this is keep in mind, positive, pure imaginary form. So this is an inductor. We know that ZL is J omega L. So to find L, we can use Z over omega. That's 200 millihenry. Question B. Similarly, you can first convert V and I into the phasor domain. Z is equal to V over I. That is 100 degrees. 100 negative 60 degrees over 4 30 degrees. And to simplify this, you can get negative 25J. And this is a pure imaginary negative value. So this is a capacitor. With the formula, we have Gc is equal to 1 over J omega C. We can find C is 1 over C times omega. That is 200 millifarads. For question C, similarly, we can calculate Z V over I. That is 100 30 degrees over 5 30 degrees. And you can get 20 plus 0J. Well, this is a pure real value. What we can know is it's just a resistor. Question 5.36. A certain element has a phasor voltage V as this, current as this, angular frequency omega is 1000 radians per second. We need to determine the nature, that's the type. So we need to determine, is it a capacitor, a conductor, or inductor, or a resistor. And we are also asked to repeat for this for question B and C. Well, so let's first do question A. Z is V over I. This calculation is much more simple compared with the last one, so we only need to directly substitute the number. 100 the angle of 30 degrees. Current is 5 the angle of 120 degrees. Simplify this, you can get 100 divided by 5, that's 20. 30 minus 120 is negative 90, and this is negative 20J. And recall what we learned from the last question. Because it is a negative, pure imaginary value, so this is a capacitor. Okay, so that's question A. Then question B. Z is V over I. And we substitute the number, very straightforward, 10 angle of 90 degrees is 10J. This is a pure imaginary positive value. So recall that's an inductor. Question C. Z is equal to V over I. Well, we substitute the number. You can see that now there's no phase, where the phase angle is equal to 0 degrees. And that's a pure real number. So we know this element is a resistor. For question A and B, we can also calculate the capacitance and inductance value. For the first question, that is 50 microfarads. For the second one is L is equal to 10 millihenry. Question P 5.38. Find the phases for the current and for the voltages of the circuit shown in figure P 5.38. And we are also asked to draw a phasor diagram and find out the phase relationship. So let's first find the phases for the current. Well, to find the current here, let's observe the what's in this circuit. So we have three elements. One is the voltage source here. One is a resistor, and the other one is an inductor. Well, so what we need to do first is to convert everything into a phasor domain. So it will be very easy for us to do the calculation for finding the current. So we have an inductor here, and we convert it into the impedance. For the inductor, we have CL is equal to J omega L. So to find the current here in the phasor domain, this is 10 to the angle of 0 degrees. So we have I, because everything is connected in series. So we have V S over R, the resistor's resistance, and the inductor's impedance, J omega L. And let's substitute the number. Vs is 10 the angle of 0 degrees over R, that is 100 ohm, plus J omega here is 500. We can, well, sometimes the question may not directly tell us the omega value, but for one circuit we can only have one omega value. So we can find it from the expressions for the elements. For example, here the expression for the voltage source gives us the omega as omega is equal to 500. So here let's substitute 500, and the L is 0.2. So now what we need is to calculate the value for this expression. You can combine this. That's 50 times 2. So this is 100J. And at the denominator, the expression is in rectangular form. So what we need to do is first to convert it into the polar form. Then it'll be very easy to calculate the current I. So we can find that I is equal to 70.71, the angle of negative 45 degrees. So we have found the current I. Now what we need to do is to find VR and VL. Well, in the phasor domain, all the elements, all the capacitor, inductor, and resistor can be thought as an impedance and can be used just like resistors. So what we need to do here is very straightforward. We only need to do is to apply Ohm's law to the currents to find the voltage value. So VR is R times I. And if we substitute the value, we can get 7.071, the angle of negative 45 degrees. And for the inductors, similarly, that's ZL times I. And the ZL is here, the J omega L. And you substitute in the value for ZL times the current I, you can get 7.071, 45 degrees. So now our task is to construct a phasor diagram. First, let's draw Vs. Vs is tan the angle of 0 degrees. So that is parallel with the horizontal axis. And the length is 10. And this is Vs. So now let's draw VL. VL has a 45 angles with the horizontal axis. So let's first draw 45 degrees. And the length is 7.071. So this is VL. Lastly, let's draw I. I has an angle of negative 45 degrees. So we go clockwise direction for 45 degrees. And this is negative 45 degrees. And because its value is 70.71, so it should be 10 times longer than the VL. Well, due to the because of the space limited, so I'm not gonna be able to draw it here. And now finally we can draw VL. VR. We know that the VR value is 7.071, so that's the same as VL. So let's draw it here. This is 7.071, and then this is VR. This is I. Well, for this relationship, we can see that we need to find the relationship between Vs and I, the phase relationship. Vs is here, I is here. Because I has an angle of negative 45 degrees with Vs, so I lags Vs by 45 degrees. One point to notice here is that because the current we use milliamp, so it's actually at a different scale for the voltage. But if we try to draw them for the same scale, the I should be a smaller value here. But if we draw it to a different scale, the arrow should be much longer for I. Question P 5.40. Find the phasors for the current and the voltages for the circuit shown in figure P 5.40. Construct a phasor diagram showing Vs, I, VR, Vc, and find the phase relationship between Vs and I. Well, this question is actually very similar to the last question. The only difference here is now we have a capacitor here, but instead of inductor. Well, so our first step is still to find the current. So to find the current, what we need to do here is we convert everything into its phasor form. So now let's do for the capacitor. So for the capacitor, we know that ZC is equal to 1 over j omega c. And because in the circuit everything is connected in series, so it's very straightforward to use Ohm's law to find the current I. So current I is that's equal to Vs over R plus Zc, and Zc is just plus 1 over j omega c. And here we convert the Vs into its phasor form, that is tan, the angle of 0 degrees. And here we can find omega is equal to 500. So let's substitute in the numbers into this expression. Have tan the angle of 0 degrees over 1000 minus 2000 j. If you simplify the denominator, you can get this expression. And similarly, to simplify this expression to a single term, what we need to do is to convert the denominator into its polar form, and it would be easy to do the simplification, and what you will get is 4.472, the angle of 63.43 milliamp. Now it's very easy to find the voltage value VR and VC. We simply apply the Ohm's law. VR is equal to R times I. That is 4.472 angle of 63.43. And we can also find the value for VC. VC is C times I. And if you substitute the number, you can get 8.944, the angle of negative 26.57 degrees volt. And then we are asked to construct the phasor diagram for Vs, I, Vr, and Vc. Well, very similarly, Vs is parallel with the horizontal axis. So here is Vs and has a length of 10. For Vr, that's here. The angle is 63.43 degrees. The length is 4.472. This is Vr. And similarly, I is also here. Because here is a milliamp, so milli times 1000, we get a voltage of 4.472. So actually here the current is much smaller, but at the same direction. So I is here. And lastly, we need to draw VC. VC has an angle of negative 26.57 degree, and VC is here. The length is 8.944. Question P 5.43. Compute the complex impedance of the network shown in figure P 5.43. And the angular frequency omega is 500, and we are asked to repeat for different omega values when omega is equal to 1000 and 2000. And we are asked to give the answers in both the polar and rectangular form. Well, so this question actually acts as for network simplification. Well, in the past, what we do is we can only combine a network of inductors or a network containing only capacitors or a network containing only resistors. But now we have a network contains all of these three types of elements. But if we can convert them into impedance, we can combine all of these three types of elements together. So now we need to compute the complex impedance of the network. So our first step is to convert everything into impedance. Well, first let's do for the inductors. Well, for inductor, we know that ZL is equal to J omega L. And for capacitors, that's ZC is 1 over J omega C. And for the resistors, ZR is just R. Well, to combine all of this together, what we can do is we find ZEQ, that's the equivalent, is equal to 1 over ZL plus 1 over ZC plus 1 over R. Well, because all the elements in this network are connected in parallel. If we recall how we combine a network of resistors, what we did is 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and plus etc. So what we do here is very similar. It's exactly the same. We are combining the impedance as what we do for resistors. So when omega is equal to 500, let's substitute in the values, and this is equal to 1 over J50 plus, because we can, for this term, we have 1 over J omega C. So that's exactly J omega C, right? So now let's become J 0.005 plus the R here is 1 over 100, that's 0.01. And you enter this into the calculator and simplify the expression. What you can get is 30 plus 7692 plus 46.1538J. And use the formulas we learned this week. We can convert it into the polar form. That is 55.47, the angle of 56.31 degree ohm. Similarly, when omega is equal to 1000, you substitute in the values and the simplified expression, you can get Z as 100 plus J0, that is 100 angle of 0 degrees ohm. And if you substitute in the omega as 2000, you have Z is equal to 30.7692 minus J 46.1538. That's in polar form 55.47, the angle of negative 56.31 degree. Question P5.45. Consider the circuit shown in figure P5.5. Find the phasors, current, voltage, and the current across each branch. And we need to compare the peak values of the IL with the peak value of IS. And try to explain the result. Let's recall what we learned from week 2 and week 3. For this type of questions, we have elements all connected in parallel. So what we first need to do is to do the circuit simplification. That's to combine the elements. So what we can do here is we can combine all of the three. They are all the same types of elements when we convert them into the impedance. So here, IS, let's first convert IS into phasor domain. IS is, because here we can use the milliamp, or the value will be too small. So if we use milliamp, we times 1,000, so it will be 10. Here, the phase is 0 degrees, so that's 0 milliamp. And we can calculate the voltage across here. Let's say that's voltage V. We can combine all of these three elements to get an equivalent impedance. That's the equivalent. And equivalent impedance is exactly just 1 over R plus 1 over J omega L plus 1 over J omega C. And we can simplify this. It's just J omega C. And we then substitute the value. And simplify this, you can get 10, the angle of 0 volts. And simply use the Ohm's law. We can find the current for each branch. So that's V over R. You can get the current flowing through the resistor to be 0 milliamp. Across the going through the inductor, that's V over J omega L. That's 550, the angle of negative 90 milliamp. For the capacitor, that's V over J omega C. That's 50, 90 degrees milliamp. Well, the thing you can find that the current, the peak value of the current flowing through the inductor is 5 times larger than the source current. The source current is here. Well, it looks a little bit surprising first, but it actually can make sense because the current in the capacitance can balance the current in the inductance. So IL plus IC is equal to 0 here. So that's why the current flowing through the inductance can be even higher than what's provided by the source. Question P5.50. So for the node voltage shown in figure P5.50. Well, so we are asked to find the node voltage. To find node voltage, we need to use node analysis. This circuit is actually pretty simple. We only have two node voltages. One is here and the other one is here. And we set this as the reference and as our ground, so we know that the voltage here is 0. So the only node voltage we don't know is V1. So we need to perform nodal analysis here by writing KCL equations at this node. assume all the currents leave that node. Well, so now we need to write the KCL equation. But before we do that, we need to convert everything into its phasor form. Well, we can see that all of the elements are written in its phasor form, but some are in the polar form, some are in rectangular form. So what we need to do, my recommendation here for our convenience in calculation, is better to convert into the rectangular form. It will be easier for us to manipulate the numbers. So let's first convert that 20, the angle of 90 degrees, into its rectangle form. That is 20j. So, and here 3, the angle of 0, that is just 3. Okay, so let's write the KCL equation. We have V1 minus 20j over 5 plus V1 here minus 0 divided by 5 plus 5j. And here we have a current source. The current provides 3 amp current, so we plus 3 is equal to 0. And we have only one unknown and one equation. We can easily solve for V1. So V1 is equal to negative 13 plus 9j. And we can convert it to the polar form. That is 15.81, the angle of 145.30 degrees volt. So now we find out the V1.